Section 14.6, Reaction Mechanisms. A balanced equation for a chemical reaction indicates the substances present at the start of the reaction and those produced as the reaction proceeds. It provides no information, however, about how the reaction occurs. The process by which a reaction occurs is called the reaction mechanism. At most sophisticated level, a reaction mechanism will describe in great detail the order of the bonds that are broken and formed and the changes in the relative positions of the atoms in the course of the reaction. We'll begin with more rudimentary descriptions of how reactions occur, considering further the nature of collisions leading to reaction. Elementary reactions. We've seen that reactants take place because of collisions between reacting molecules. For example, the collisions between molecules of methyl isonitrile can provide energy to allow the isonitrile to rearrange. Similarly, the reaction of nitrogen oxide and ozone to form NO2 and O2 appears to occur as a result of a single collision involving suitably oriented and sufficiently energetic NO and O3 molecules. Both of these processes occur in a single event or step that are called elementary reactions or elementary processes. The number of molecules that participate as reactants in an elementary reaction defines its molecularity. If a single molecule is involved, the reaction is unimolecular. The rearrangement of methyl isonitrile is a unimolecular process. Elementary reactions involving the collisions of two reactant molecules are bimolecular. The reaction between NO and O3 is bimolecular. Elementary reactions involving simultaneous collisions of three molecules are termolecular. Termolecular reactions are far less probable than unimolecular or bimolecular processes and are rarely encountered. The chance that four or more molecules will collide simultaneously with any regularity is even more remote. Consequently, such collisions are never proposed as part of a reaction mechanism. Multi-step mechanisms. The net change represented by a balanced chemical equation often occurs by a multi-step mechanism, which consists of a sequence of elementary reactions. For example, consider the reaction between NO2 and CO. Below 225 degrees, this reaction appears to proceed in two elementary reactions, or two elementary steps, each of which is bimolecular. First, the two nitrogen dioxide molecules collide, and an oxygen atom is transferred from one to another. The resultant NO3 then collides with a carbon monoxide molecule and transfers an oxygen atom to it. Thus, we say that the reaction occurs by a two-step mechanism. The chemical equations for elementary reactions in a multi-step mechanism must always add to give the chemical equation of the overall process. In the present example, the sum of the two elementary process reactions is. Simplifying this equation by eliminating substances that appear on both sides of the arrow gives equation 1423, the net equation for the process. Because NO3 is neither a reactant nor a product in the overall reaction, it is formed in one elementary reaction and consumed in the next, it is called an intermediate. Multi-step mechanisms involve one or more intermediates. Rate laws for elementary reactions. In section 14.3, we stress that rate laws must be determined experimentally. They cannot be predicted from the coefficients of balanced chemical equations. We're now in a position to understand why this is so. Every reaction is made up of a series of one or more elementary steps, and the rate laws and relative speeds of these steps will dictate the overall rate law. Indeed, the rate law for a reaction can be determined from its mechanism, as we'll see shortly. Thus, our next challenge in kinetics is to arrive at the reaction mechanisms that lead to the rate laws that are consistent with those observed experimentally. We'll start by examining the rate laws of elementary reactions. Elementary reactions are significant in a very important way. If a reaction is an elementary reaction, then its rate law is based directly on its molecularity. For example, consider a unimolecular process. A forms products. As the number of A molecules increases, the number that react in a given interval of time will increase proportionally. Thus, the rate of a unimolecular process will be first order. Rate equals K times the concentration of A. In the case of the bimolecular elementary steps, the rate law is second order, as seen in the following example. A plus B yields products. The rate equals K times the concentration of A to the first power times the concentration of B to the first power. The second order rate law follows directly from the collision theory. If we double the concentration of A, the number of collisions between A and B will double. Likewise, if we double the concentration of B, the number of collisions will double. Therefore, the rate law will be first order in both A and B and second order overall. The rate law for all feasible elementary reactions are given in Table 14.3. Notice how the rate law for each kind of elementary reaction follows directly from the molecularity of the reaction. It's important to remember, however, that we cannot tell by merely looking at the balanced chemical equation whether a reaction involves one or several elementary steps. The rate determining step for a multi-step mechanism. As with the reaction in sample exercise 14.13, most chemical reactions occur by mechanisms that involve two or more elementary reactions. Each of these steps of the mechanism has its own rate constant and activation energy. Often one of the steps is much slower than the others. The overall rate of a reaction cannot exceed the rate of the slowest elementary step in its mechanism. Because the slow step limits the overall reaction rate, it is called the rate determining step or the rate limiting step. To understand the concept of a rate determining step, consider a toll road with two toll plazas. We will measure the rate in which cars pass through the second toll plaza. Cars enter the toll road at point 1 and pass through toll plaza A. They then pass an intermediate point 2 before going through toll plaza B and arriving at point 3. We can therefore envision the trip along the toll road as occurring in two elementary steps. Point 1 to point 2 through plaza A, and step 2, point 2 to point 3 through plaza B. The overall is point 1 to point 3 through both plazas A and B. Now suppose that several of the gates at toll A are malfunctioning, so that the traffic backs up behind it as depicted in figure 1418A. The rate at which cars can get to point 3 is limited by the rate at which they can get through the traffic jam at plaza A. Thus, step 1 is the rate determining step of the journey along the toll road. If, however, traffic flows quickly through A but gets blocked up at plaza B, as depicted in 1418B, the number of cars builds up in the intermediate region between the plazas. If this case, step 2, the rate is determining. At the rate at which the cars can travel the toll road is limited by the rate at which they can pass through plaza B. In the same way, we say the slowest step in a multi-step reaction limits the overall rate. By analogy to figure 1418A, the rate at the faster step following the rate determining step does not speed up the overall rate. If the slow step is not the first one, as in 1418B, the faster preceding steps produces intermediate products that accumulate before being consumed in the slow step. In either case, the rate determining step governs the rate law for the overall reaction. Mechanisms with a slow initial step. We can most easily see the relationship between the slow step in a mechanism and the rate law for the overall reaction by considering an example in which the first step in a multi-step mechanism is the slow, rate-determining step. As an example, consider the reaction between nitrogen dioxide and carbon monoxide to produce nitrogen monoxide and carbon dioxide. Equation 1423. Below 225 Celsius, it's found experimentally that the rate law for this reaction is second order in nitrogen dioxide and zero order in carbon dioxide. So the rate is nitrogen dioxide squared. Can we propose a reaction mechanism that is consistent with this rate law? Consider the following two-step mechanism. Step 1 is slow, step 2 is fast. Step 2 is much faster than step 1. That is that K sub 2 is much bigger than K sub 1. The intermediate nitrogen trioxide is slowly processed in step 1 and is immediately consumed in step 2. Because step 1 is slow and step 2 is fast, step 1 is the rate determining. Thus, the rate of the overall reaction depends upon the rate of step 1, and the rate law of the overall reaction equals the rate law of step 1. Step 1 is a bimolecular process that has the rate law, case of 1, of N2 squared. Thus, the rate law predicted by this mechanism agrees with the one observed experimentally. Carbon monoxide is absent from the rate law because it reacts in a step that follows the rate determining step. Mechanisms with a fast initial step. It's less straightforward to devise a rate law for a mechanism which has an intermediate is a reactant as the rate determining step. This situation arises in multi-step mechanisms when the first step is fast and therefore is not the rate determining one. Let's consider one example, the gas phase reaction of nitric oxide with bromine. The experimentally determined rate law for this reaction is second order in nitric oxide and first order in bromine. We seek the reaction mechanism that's consistent with this rate law. One possibility is that the reaction occurs in a single termolecular step. As noted in practice exercise 14.3, this doesn't seem likely because termolecular processes are so rare. Let's consider an alternative mechanism that does not invoke a termolecular step. In this mechanism, step 1 actually involves two processes, a forward reaction and its reverse. Because step 2 is the slow rate determining step, the rate law for that step governs the rate of the overall reaction. The rate equals K times the concentration of NOBr2 times the concentration of nitric oxide. However, NOBr2 is an intermediate generated in step 1. Intermediates are usually unstable molecules that have low unknown concentration. Thus, our rate law depends on the unknown concentration of an intermediate. Fortunately, with the aid of some assumptions, we can express the concentration of the intermediate in terms of the concentration of the starting reactants. We first assume that NOBr2 is intrinsically unstable and that it does not accumulate to a significant extent in the reaction mixture. There are two ways for NOBr2 to be consumed once it's formed. It can either react with the nitric oxide to form NOBr or reform nitric oxide and bromine. The first of these possibilities is step 2 is a slow process. The second is the reverse of step 1, or unimolecular process. Because step 2 is slow, we assume that most of the NRBr2 falls apart according to equation 1428. Thus, we have both the forward and reverse reactions of step 1, occurring much faster than step 2. Because the forward and reverse process of step 1 occurs rapidly with respect to the reaction in step 2, they establish an equilibrium. We have seen examples of dynamic equilibrium before in the equilibrium between a liquid and its vapor and between a solid solute and its solution. As in any dynamic equilibrium, the rates of forward and reverse reactions are equal. Thus, we can equate the rate expression for the forward reaction in step 1 with the rate expression for the reverse reaction. Solving for NRBr2, we have substituting this relationship into the rate law for the rate determining step equation 1427, we have rate equals K2 over K1 over the reverse of K1 times the concentration of nitric oxide squared times bromine equals K NO squared Br2. This result is consistent with the experimental rate law. The experimental rate constant K equals K2 K1 over K negative 1. This mechanism, which involves only unimolecular and bimolecular processes, is far more probable than the single termolecular step. In general, whenever a fast step precedes a slow one, we can solve for the concentration of an intermediate by assuming that an equilibrium is established in the last step.